Now I would request Mr. P.V. Ramaya, Council Member, Chennai Chapter IAF, to introduce our third speaker of the day, Mr. T.S. Rao, COO Foundry, Madras Engineering Foundry Division, to our audience.
I will be privileged to introduce third speaker, Srinivasa Rao T.S. Rao. His education is Diploma in Draftsmanship and Design, Masters in Public Personnel Management, MBA in TQM, certifications Certified Lead Auditor for almost all certification including PED, Dell Trained Leader, Lean Six Sigma Black Belt, experience 36 years of Foundry experience in all processes including sand casting, centrifugal casting, gravity die casting, last wax, last foam and replicant and material including irons, steel and copper alloys, with hands-on experience in new product development. Travel to over 14 countries for supporting foundry suppliers and quality and productivity improvements. Developed over 2,000 products from APQP to PPAP. 20 years in Hindustan Foundries Hyderabad and 1 year in Hindustan Motors Calcutta. 2 years in Daxin Foundry Bangalore. 1 year in Pitti Castings Hyderabad. 12 years in Armstrong Field Technology Bangalore. Recently joined in Madras Engineering as a CEO. Thank you. Welcome, sir.
So I'm happy today to share my knowledge on the gating system. You know, the gating system is an ocean. So I was given only 20 minutes. I don't know how I justify the knowledge sharing in 20 minutes, but I do my level best. You know, the gating system is a vital in any foundry industry. You know, the generation we are here, we know earlier the gating system, we thought it is art. It is a tribal, it's a tribal knowledge. The art is in the mind. The later, now we have the simulation software, we found that it is a science. The generation we are sitting here, we are between arts and science. Okay, let us continue this to save the time. Introduction. So we know the gating system is a channel which is created to pass the molten metal into the casting cavity. So the gating system again depends on the material, depends on the boundary conditions, depends on the processes what we choose for. The objectives remain constant irrespective of the material and the molding practice. We have to fill the mold cavity within the shortest possible lead time. Then you need to get a higher yield, like optimum number of the pattern cavities on the given pattern plate. And the less rejections, sound casting, good surface roughness, less fettling or less rework, and geometry and aesthetics are not compromised because of the gating. So these are the basic inputs for calculating the gating design, the material of construction and the beta. The beta is again material specific. If you see the gray iron, the beta is not significant. If you see the ductile iron, beta is significant. If you see the steel grades, the beta is more significant. The wall thickness of the casting, what you are going to develop, the raw part weight, the modulus, and the significant modulus. You know, the modulus is the volume by the surface area. The significant modulus where the hot zones with the last freezing area is called the significant modulus zone. The pattern layout and the casting process, the process where we are going to pour our casting. And from the molding process, we need the type of molding, what type of molding, whether it is a green sand, chemically bonded mold or metal mold, then the pouring height from the casting, then the pouring temperature and mold filling time. These are the, like table shows how do you calculate the modulus, the simple geometrical shape, the modulus can be directly derived from the tables. If it is complex, we need to go with the simulation software which is called L0 analysis where we find the significant modulus. We also can calculate the modulus. When you get to the next slide, the type of gating, there are two significant the gating types. One is pressurized, another is non-pressurized. The pressurized gating, the difference between the pressurized or non-pressurized is the choke. Where do you keep the choke? If the choke is near the casting, it is called pressurized gating system. If the choke is near the downscrew, the gating system is called non-pressurized gating. Again, depends on the wall thickness, depends on the molding practices. We need to select what type of the gating system we need to incorporate. Moving on, the gating calculation. There are numerous tables are available, numerous calculations are available for calculating the gating. But we need to customize, we need to select what is suitable to our requirement, and we need to try out whatever is the best we need to follow. Gating ratios, this is very, very important. Whatever the calculation you choose, that only give you the volume of the choke. From the volume of the choke, we need to redefine, like what's from the in-gate, and then what would be the runner, what would be the offset, and what would be the down screw. And these are the typical, the gating ratios for the ductile iron, and these are the typical the gating ratios for the gray iron. So these are to be followed to achieve the benefits what we have targeted in this slide 2. These are the parts design. These are very important. The first one is the down screw. The down screw, this is the shape, the typical shape of the down screw for withdrawal of the mold. And the bottom is called sprue well, sprue cup or sprue well. And next one is the runner bar. The dimensions of the runner bar is 1:2, where the 1 is the width and 2 is the height, and some foundries makes it taper to have the higher yield. Then some of the foundries will have a slag trap at the end of the runner for collecting the slag. The next one is a riser and the riser neck. Riser again, the dimensions are the 1:1.5. When the diameter is 1, the height can be 1.5 or maximum 2. It cannot go beyond 2. And the bottom is a riser base. Then is the in-gate. The in-gate again, it is 1:4. The length is 4 and the height is 1. And this is the neck which is connected to the casting. The chamfer is given so that the gating will not break inside the casting. These are the flow-offs. There are different shapes of flow-offs you can have. It can be round, it can be square, or it can be rectangle, and it has to be tapered down for the mold release. So these are the feeders. You know, the feeders are important for feeding the significant modulus, where in ductile iron or stainless steel. The first one is chill. We need to select the feeders based on the modulus extension factor, which is important. If the chill is the modulus extension factor is only 0.5, if it is insulating sleeves, and these are also called direct pour sleeves, the modulus extension factor is 1.5. Next is the insulating the exothermic sleeves, where the MEF is 1.67. The high density sleeves, the MEF is 1.75. And this is the purpose of the chill. The purpose of the chill, it doesn't feed, it only promotes the cooling. It promotes the cooling and push the hot metal away from the chill zone. And these are the type of filter. There are two types of filters available in the market. One is the pressed or extruded ceramic filters. And again, it depends on the PPI, the porous per inch. Then next is a ceramic foam filter or honeycomb filters. The lot of tables are available for selection of the filters. This is the purpose of the filter. It is like a tea filter. So when the metal with contamination or the foreign particles pass through the filter, only clean metal goes inside the casting cavity. This is the basic casting design. So if you see the layout, like when you pour the liquid metal in the pouring basin, again the pouring basin, we can have a different shapes, depends on the foundry practice. Then the metal gets into the down screw, goes into the well. Then there is a filter. After passing the filter, then there is a offset. From the offset, there are runner bars. From the runner, the metal goes inside the casting or to the risers. Chills are placed over here. The risers, the exothermic sleeves are placed over the flanges, and these are the flow-offs. This is a typical gating system for the horizontal chemically bonded sand molding system. This is called pressurized gating system. So when you pour the liquid metal, the first metal which has to pass through the flow-offs, so that if any foreign particles or the sand particles with the loose particles will get into the flow-offs and goes outside, and the clean metal stays inside this. While solidifying, the risers feed the casting. So these are the simulations. Thanks to the simulation softwares we have available now. Like the first one is the filling. So you can see the temperature here. So right from 1123 to 1400. From the color code, you can make out what temperature it is. See, the hottest zones The hottest temperature is in the down sprue, the hottest temperature is in the risers, because these are exothermic, they retain the temperature for long time. So next one is on the velocity. Velocity is very important with respect to the casting quality. The higher the velocity, the higher the turbulence in the mold cavity, higher the inclusions in the casting cavity. So again, the velocity, it can be defined by the graphical form here. This color being the 0 and this color being 2. Any velocity, if it is beyond 1.5, it is dangerous. So normally, if you see the higher velocities in the ingates, because these are the chokes. We can also identify where the choke is in the whole gating system. The velocity is important with respect to having a sound casting and filling time. Next one is the solidification. So this is also called directional solidification. Here you can find out like how the casting gets solidified. So we know the thin wall starts solidifying first, and where the chill is connected, because chill is conductive, you can see it gets solidifies first, then the directional solidification, and also we can see the isolated spots in the casting cavity. So wherever it is solidifying last, if it is not connected to the feeder, you can see the zone. If it is not connected, we end up with a shrinkage here. Similarly here, if it is not connected to the riser, the isolated spots in the casting, we end up with a shrinkage. So moving on to the air entrapment. So when you before pouring the metal into the casting cavity, it contains some amount of air and some amount of the gases. When you pour liquid metal, so we have to take care in the gating system when the metal in, the gases out. So this is also we can see how the air is getting pushed out through the topmost portion of the casting cavity, through the flow offs and through the risers. So again, we can see the air entrapment in the graphical form. Next slide is on the voids. The voids is like unfilled the pockets. So this also we can see in some cases, like if it is not, gating is not properly connected, you can see there is some amount of void, it is created initially, and then it gets pushed out later. So that also we can simulate, and then gating can be corrected accordingly to ensure that there are no voids. The shrinkage, so when the casting is getting solidified, we can see the hot spots in the casting. Again, the hot spots can be defined with respect to the graphical form, like this, when it is divided from 0 to 100, this is a level 1 to level 5. The first 20 are considered as a level 1 radiography defect levels, and up to 40 is a level 2, up to 60 is like level 3, up to 80 is level 4, and 100 is level 5. If you see the casting cut section, we can make out from the casting color, the cut section color, the whole casting is well within level 1 or level 2. So this is the indication that we can find out. Now the simulation, the casting, the simulation softwares are more advanced. We can even check the hardness at the given point of time. We can check the microstructure. We can check a lot of other parameters. This is a virtual foundry. Like, the simulation software is virtual foundry that saves the number of iterations in the shop floor. Moving on to the next slide, these are the beautiful castings produced in various processes. These are all developed by me in my previous organizations. The first one is the centrifugal castings, the copper alloy castings, the sand casting. This is the gravity tie casting. This is the last form technology. This one also in the last form technology. And this is the stainless steel produced in replicast technology. So it shows the casting it represents how good the gating design is. So is the last slide. Just because we have DSLR doesn't mean that we are the photographer. So this applies to the Foundrymen because we think like we have software. The simulation software is like a laboratory. When you give the blood sample, the vitals, it only gives the vitals. It says this is your hemoglobin percentage or this is your other parameters. It will not tell you how you fix it. So it is up to us. How do you fix it? By taking the parameters from the laboratory, we need to fix it. The advantage is instead of fixing in the shop floor in the earlier days, we have an opportunity to fix it in the software. We can reduce the number of iterations by using the simulation software. So we can do any number of iterations in the software unless we are fully confident that we are going to do right first time. Thank you so much. This is my last slide. If you have any questions, we can connect on this. Hope I could finish on time for the committee. Thank you so much. If you have any questions, I'll be
Any
happy to
questions,
answer.
anyone?
See, pressurized, as I said, that the choke, which is connected to the casting cavity. Okay, I'll tell you. The pressurized is required for the low wall thickness castings, and it is not suitable for green sand because the green sand mold is very soft. So, in the pressurized gating system, the green sand, the mold is likely to wash away because of the velocity of the metal, and then the sand particles will stuck in the casting. So it depends on the wall thickness, depends on the molding practice. We need to select either pressurized or non-pressurized. Normally, for cylinder blocks, pressurized gating is used. For other castings, non-pressurized. For green sand, non-pressurized. PPI depends on 10 PPI or 20 PPI, depends. Normally for a gray iron, you can go for ceramic, which is cheaper. Normally for ductile iron, you can go with honeycomb filters. These are little expensive, but they are more effective.
Now people are focusing on more yield. So there is a discussion about the riserless casting.
Riserless casting, so they are many, we have a lot of, we have a lot of the feeders. Riserless casting, it is called fed pour or direct pour. We can directly pour on the casting. The highest yield I achieved is 98.2%. Even today, that is a record in Indian history. 98.2% is the highest yield we achieved. 98.2. That is the highest yield which is recorded in the in the industry in India today. It is a direct pouring. The casting weight is 450 kilograms. We directly poured on top of the casting through the direct pouring sleeve. Optimum yield, it depends. As I said, 98.2 is a challenge for us. So optimum, I achieved at an average, the ductile iron yield is 85%. Sorry, gray iron yield is 85%, ductile is 75%. That is the average yield I achieved in my previous organizations.
Any other questions? Thank you, sir. That was a lovely presentation.
Thank you so much. Thanks for your time.
First, I need to thank him. He recalibrated his presentation quickly to 20 minutes, the minute I asked him to do. So thanks again, sir. And a very, very technically sound presentation on gating calculations. And a lot of simulations were shown to us. And from the number of questions he received, I guess we all benefited from his technical information. So thank you again. Now I invite Mr. Madhu Boja, Council Member, Southern Region IAF, to facilitate Mr. T.S. Rao with a memento and Angavastram.